Hi everyone, this is our video example related to our lecture on the energy balance for a closed system. This is question 7.13 on page 384 of your textbook. Go ahead and read up the question first and then follow along with this video example. So in this case, we have a piston-filled cylinder with a 6 centimeter inner diameter, and it contains 1.40 grams of nitrogen. The mass of the piston that is on top of the cylinder is 4.50 kilograms, and on top of that, you're going to add a 25 kilogram weight on top of this piston. We are given that the gas temperature is at 30 degrees C, the pressure outside the cylinder is 2.5 atmospheres, and in part A, we're going to prove that the absolute pressure of the gas in the cylinder is 3.55 times 10 to the power 5 pascals. Then calculate the volume occupied by the gas, assuming that this gas is ideal. So here's a visual of what's going on. We have this cylinder that is 6 centimeters in diameter. It contains 1.40 grams of nitrogen. You have this piston that weighs 4.5 kilograms, and on top of that, you add another 25 kilogram weight. What are the other things involved? Within the gas, inside the gas, or the nitrogen is going to exert some pressure, so I'm going to call that P gas. And on the outside, you have some outside pressure that is pushing down as well. And that is, I'm going to call it as P sub outside. So to calculate the absolute pressure of the gas, or to prove that is the value that's stated in the question, we're going to do a force balance. So going back to physics, this is at equilibrium, so the piston is not moving, which means all the forces that are pushing this piston down is equilibrated by all the forces that's pushing this piston up. And so what are the forces that are pushing it down? You have the pressure from the outside, and you have the two weights. And in terms of what is holding this piston back up, and that's just the pressure exerted by the gas. So here's our force balance. We have the weights, the overall weight, which is the piston plus the 25 kilogram weight. We have the outside air, and that has to be equal to, or that is held up by the gas in the nitrogen gas that's in the cylinder. Now what you see down here is that you have the weights, which is a force. Well, we have the weights for now. We need to multiply that by our gravitational acceleration. In terms of pressure, pressure is a force per unit area. So we need to multiply that by A, which is the area that's exerted by this pressure. And in this case, it will be the cross-sectional area of the cylinder. So now let's put in the different numbers that we have. Here are our weights of our piston and our weight. This is in kilograms, and so to get it to a force or to a weight, we need to multiply by 9.81. And on the right-hand side, what I've essentially done is move this term over to the right-hand side and factor out the A, because the cross-sectional of the cylinder is constant and it's the same area there. So that's our area of our cross-sectional area of our cylinder, and we have P gas minus the P outside. We're going to do everything in SI units, so I'm converting 2.5 atmospheres to SI units. From there, I can solve for my P gas, and you can show that it is 3.55 times 10 to the 5 pascals. Okay, once we have the pressure of the gas, to calculate the volume occupied by the gas, assuming ideal gas behavior, just use the ideal gas law. Before we can do that, we need the number of moles of the gas. We have the mass. We divide that by the molecular weight. We have 0.05 moles of nitrogen. Now we can use our ideal gas law, V equals to nRT over P. Make sure that the units are consistent. I like to do my ideal gas law in SI units, so I know for sure it's going to come out in SI units. By keeping everything consistent, we know that I'm going to get meters cubed, and we can convert from meters cubed to liters. And so we have 0.354 liters of gas. All right, so now part B is where we start to do our closed system energy balance. So suppose the weight now is removed, so the 25 kilogram weight is now going to be removed, and the piston is going to move, so the gas is going to expand. We're going to assume that the process takes place in two steps. One is a rapid step where we have a negligible amount of heat exchange with the surroundings, and then there's a slow step in which the gas returns back to 30 degrees C. So considering the gas as the system, we want to write the energy balance for step 1, step 2, and the overall process, and we are told that we can neglect our change in kinetic energy and our change in potential energy. So let's do that first, and then we'll look at the last part of the question. In this first step, we see that we're going to start with our general balance, energy balance. We're told to neglect kinetic and potential energy changes, so we have that. We are also told that negligible amount of heat is exchanged, so that means our Q is 0. And our simplified energy balance is simply delta U equals to W. So now let's look at step 2. Similarly, we have our kinetic and potential energy changes to be negligible. Now in this case, we have, that's all we have essentially. So there's nothing else that we can simplify. And so in our step 2, our energy balance simplifies to delta U equals to Q plus W. What about the overall process? In terms of the overall process, same thing, we have our energy balance, neglecting kinetic and potential energy changes. But we said that at the start, it is at 30 degrees C. Following these 2 steps, the gas returns to 30 degrees C. There's no phase change, there's no temperature change, which means our delta U is 0 as well, since there's no compositional change, temperature changes, phase changes. And so the overall process, the energy balance is actually Q plus W is equals to 0. All right, now let's look at that last line in the question for part B. If U hat varies proportionally with T, so we haven't talked about U hat yet, so this idea of hat is our specific internal energy. So it is essentially the internal energy per mass of the system or per mole of the system. If we are given that the specific internal energy varies proportionally with T, does the gas temperature increase or decrease in step 1? And we want to briefly explain that answer. So we're going to start with our energy balance in step 1. We see that delta U is equals to W. But we know that here, because we remove the weight, the gas is expanding. So work that is done by the gas, by convention, work done by the gas is negative. That means our W is negative, which means our delta U is negative, which means the internal energy is actually dropping. For internal energy to drop, that means our temperature is actually decreasing. So that's how you would rationalize what's going on with the temperature based on our energy balance. All right, we have one more part to this question. So we are told that the work done by the gas equals to the restraining force times the distance traveled by the piston. So how much work is done by this gas? It is equal to the force multiplied by the distance moved by this piston. We want to calculate this quantity to determine the heat transfer to or from the system during the process. So essentially using our overall energy balance that we have from part B. So what we're trying to calculate down here, we're trying to calculate a change in the volume, which means we want to calculate this delta Z as this piston moves up. We know it's the cross-sectional area, so if we know how much it moves, we know how much the volume changes. And so to do that, we need to find the final pressure. If we know the final pressure, we can use our ideal gas law, find the final volume. We know the initial volume, we can find a change in the volume. And from that, we can find a change in our height. So how are we going to find this delta V? We are going to, or how are we going to find this final pressure? We're going to do the same thing. We're going to find our force, we're going to do a force equilibrium at this final state. So on this final state, the only difference down here is that down here we have removed the weight. So the weight term now here is just simply the piston. That's all we have down here. Putting in the numbers, we only have 4.5 kilograms on the left-hand side. Everything on the right-hand side looks exactly the same. And now we can find the pressure of the gas in the final state. We find it as 2.689 times 10 to the power 5 pascals. And so with that, we can find the final volume. Again, using our ideal gas law, the final volume is 0.468 liters. We know the change in volume. We can find the delta Z. Delta Z is just the change in the volume divided by the cross-sectional area of the cylinder. Putting in all the numbers, converting it to SI units of meters, and we find that essentially what has happened is this piston has moved by a distance of 0.04 meters in the process. All right, so now we have calculated the delta Z. We want to calculate this work done. We said that the work done is equal to the force times the distance moved. So work done by the gas, it is, as it's expanding, what is it doing work against? Is work against moving this piston upwards, which has some weight, and moving, basically doing work against the pressure that's pushing it down. Writing it in terms of math or an equation form, the work done against the piston essentially is the weight of the piston multiplied by the change in the distance this piston has moved. And the work done against the outside pressure is the pressure multiplied by the cross-sectional area. We have all of these already calculated, so let's just put in the numbers, keeping everything in SI units. I can calculate this whole thing in SI units and I get 30.4 joules. So this is the work done by the gas. If we put it into our equation or our energy balance, you will see that because work done by the gas is negative, so the W term is actually minus 13.4 joules. Work done by the gas is negative. So now we can calculate the heat transfer. If you go back to our overall equation, energy balance equation, we have simplified it to Q plus W equals to 0. We know W is minus 30.4 joules. So Q is 30.4 joules and is positive. So in this case, we see that heat is transferred to the gas from the surroundings. So that's all we have for this example. Work hard, be smart, and I will see you in the next lecture where we're going to talk about our open system energy balance.